I'm talking about how to write a chess program in Python. I've done this as a Jupyter notebook with code inserted in it, and at the end of the talk we'll have seen all of the code, and we should have a working chess engine.
Do you have a mic?
Oh yes, I need a mic. Yes, that was a good idea. Turn on the mic. Is this on?
Yes.
Yeah. Okay, you can all hear me?
I can't see your text. Could you make it bigger, please?
Probably, but then I may run out of space on the screen. But I'll give it a go. Command plus. And minus. Better? Okay. Bigger?
Yes, thank you.
Okay. Right. How do I make it full screen? F12?
F11.
This is where I show off that I don't often give talks. This is my first talk ever, but hey, I can't do that, so I'm going to downsize one. Sorry about this. And minus. And then I have enough space. Okay, that's the best I can do. Okay, so why is chess an interesting problem? I'm going to talk about how to represent a board as a Python data structure. I'm going to give you a print function for a board, because this is useful for debugging. I'm going to talk about how you evaluate whether a chessboard is a good position for white, good position for black, how much white or black are winning by, and then I'm going to talk a little bit about how to do a tree search, so how to look at all the possible moves, evaluate them, and all the possible moves from there, evaluate them, and figure out what's the best possible move you can make at any given time. And at the end, there should be a live demo where a game of chess plays out where the computer plays itself. I said in my talk introduction that I was not going to depend strongly on an existing knowledge of chess. So the basics of chess is that it's a two-player competitive game. One player is white, one player is black. Players take turns to move their pieces on an 8x8 board, and the player wins if they get to a point where the capture of the opponent king is certain, and you lose if your king ends up in a position where it's certain to be captured. This is called checkmate. I am going to be simplifying things slightly today, so I'm not going to be covering things like stalemate. That's just to make sure that things fit into the time available. A chessboard will look something like that in the initial state. And ideally that will all fit on the screen at the same time, but why is chess an interesting problem? It's naturally competitive, and chess engines are simple enough that you can build one in your free time. You can build a simple chess engine in your free time, and you can then keep optimizing it forever and ever and ever. There is no natural endpoint to how much you can optimize your chess engine or how strong you can make it. And there's a lot of literature produced by smart people on how to write good chess programs. And I personally take interest in this topic because I had a competition in Christmas 2016 where I competed with my brothers and tried to see who could write the best chess engine, and I won, so I was quite happy. Right, board representation. Now, in a strong chess engine, speed is really important, but today I'm going to go for the simplest possible representation of a chessboard. Because chessboards are naturally two-dimensional, I'm going to go for a list of lists, and each square I'm going to represent with a single character. And I'm going to say that kings are K, queens are Q, rooks are R, bishops are B, knights are N, and yes, I do know that knight doesn't begin with an N, but it means it doesn't conflict with kings, and pawns are P. And I'm going to say that white pieces are uppercase, and black pieces are lowercase. And this means we also get to check whether a piece is a white piece or a black piece by checking whether it is up or is lower, which is a Python built-in, which is kind of nice. Okay, so an initial board looks something like that. There's not much to say about that, that's a standard board. I like this representation because it's very easy for humans to look at and understand, but then I define a function that I can convert that easy to understand representation into a list of characters. That little function there. And I run this. I get my initial board as a list of lists. This isn't particularly human readable, but we can easily operate on it. So here is getting a piece from it, in this case from the 7th seventh row, fourth column, and that's a king. And we can do lookups fast enough that we can write a reasonable engine. In this particular case, it takes 78 nanoseconds to do a lookup. Oh, the timeit library is really, really useful for optimizing small pieces of code. I used it extensively when I was trying to write a competitive chess program, because the faster you can make your chess program, the stronger it plays. Here's a demo of it, looking whether the piece is up or is lower. As in, is it uppercase or is it lowercase? And hence, is it white or black? And that's also reasonably fast. I define a function to print my board. This is just joining together my lists of lists with some new lines. And I can prove that I get back the same board that I started with, which is always nice. I'm going to be using that print board function a few times later. Right, so when you're trying to decide what move you should make, you need to be able to decide whether the resulting board would be good or bad, and by how much. So you need some kind of way to quantify the value of your chess position. Now, human chess players normally go with the following board valuation. Pawns are worth 1, rooks are worth 5, knights are worth 3, bishops are worth 3, queens are worth 9, and kings are kind of infinite, because if you end up in a position where you're going to take the king, you win the game. And then humans normally have a kind of fuzzy evaluation of how good a position is. But we need to numerically define how good a position is. So I'm going to switch to a slightly different board evaluation. I'm going to do all my board evaluation in centipawns. This means I get to do everything in integers, and centipawns are kind of traditional in the world of computer chess. And I'm going to make white pieces positive and black pieces negative. This means that I can evaluate whether a board is good for white or good for black just by adding up all of the pieces that are on the board. And if it's a positive number, it's good for white, and if it's a negative number, it's good for black. And I make my king worth 200 pawns. It just needs to be bigger than the value of anything else that's on the board. And then your chess engine will try and optimize for taking the king over everything else. This is the same information here as in the table. It's just as a dictionary. Note, I'm using dot to mean a square with nothing on it, and that's worth 0. Empty squares are not good for either side. They're not worth anything. If I just use this evaluation of what pieces are on the board, it's a crude approximation to the value of the position. But to get better play, we also need to evaluate where the pieces are, because that contributes quite a bit to who's winning. So I define a set of positional values in centipawns for each of the pieces that describe how much a piece is worth in a particular position. So here you can see the further up the board that your pawn gets, the more valuable it becomes. Pawns that are close to the opponent's back row are worth maybe 50 centipawns more than normal. And knights benefit from being in the middle and don't like being in the corners. Bishops benefit from being in the middle a little bit. Rooks, it doesn't really matter much where they are. Queens benefit a small amount from being in the middle, but because queens can move around so fast, they don't have strong benefits according to where they are on the board. Kings are a bit weird. So kings, early in the game, it's beneficial for them to be at the back and at the sides, and then late in the game, it's beneficial for them to be in the middle where there's lots of space to move around. But for the sake of simplicity, I'm not going to cover that. I'm just going to say that kings have no positional value regardless of where they are. And empty squares also have no positional value according to where they are. And I'm representing that as it's worth 0 for every position, for every x, and 0 for every y. Right. Now, later on, I'm going to evaluate how good a board is by adding up the value of all the pieces on the board and the value of their positions. But I can save time computationally so I can save compute time by pre-calculating the piece values plus the position values. So I'm just going to add the piece values onto the values of their positions. And I'm also going to duplicate the piece values for black and rotate it around. So black's piece values are the other way round from white's piece values. So black pawns get more valuable as they move toward white's back line. This produces a big table, which I'm not going to talk too much about because it's quite repetitive. I just want to note that, for example, the white king, which I'm using capital for king, has a positive value, the black king has a negative value, and the empty piece has no value everywhere. This means we can define an evaluation function for who's winning the game and by how much. This takes a board, which is a list of characters, and returns an integer that describes who's winning and by how much. And this is simply a sum of the position value of whatever is at an xy position, given that it is at an xy position for every x in 0 to 7, for every y in 0 to 7. And this is just a summation of everything that's on the board. And the initial board, which I'll go back and demonstrate, the initial board is symmetrical, so you should expect that the evaluation function evaluates it to say neither player is winning at this point. And our evaluation function does indeed return 0, which is encouraging. We haven't screwed up yet. Okay, so then I'm going to make a move. This is a king pawn forwards 2. This is a white move. And then I'm going to convert that to our list representation. There we go. And if we evaluate the first move, we should have white in the lead, because white has moved a pawn forwards, and thus white is in a slightly better position. And when we evaluate it, we find that white is now winning by 40 centi-pawns. And if you're a chess player, that probably makes sense. Actually, how many of you guys play chess? Can you just put your hands up? Oh, okay, so most of you. So that's helpful. I wasn't sure how much chess knowledge to assume in the audience, because not everybody plays chess. Okay, so I'm going to define a function that makes a move. This takes a piece from an xy position and moves it to an xy position. And it takes a board as well, and it returns a board with the move made. And this is just going to copy the board, move the piece, and remove the piece from the old position. And I'm going to programmatically do the generation of the second move, do generation of a second move, given the first move, and a particular set of coordinates for the move. And I can print that and demonstrate that the black pawn to move forwards to, which is what I intended. What am I doing for time? I think I'm okay for time. Yeah, I'll make move functions simpler. Right, move generation. So we need a function that takes in the current state of the board and returns a list of all possible future boards after one move has been made. This is unfortunately complicated because the rules of chess are complicated, so mostly I'm going to skip this. I just define the ways that the pieces can move, and there's lots of logic for pawns. Pawns are odd. I'd love to cover that in more detail, but we simply don't have time, and it is kind of boring, so I probably shouldn't cover it. I'm going to generate, for my second move, I'm going to generate a list of all possible third moves. I'm going to pick out one of the elements of the list, the first element. I'm just going to print it using the print board function I defined earlier. And it is a valid move for white. Pawn forwards more. And there's 31 possible moves in this position. This is actually quite typical for a game of chess. In most board positions, there's around about 30 moves that are possible. Okay, what's the best move if I search one move ahead? So, given that we are in the given that our board looks like that, let's create all the possible moves and evaluate how good they are and pick the best one. So this is for every move in possible third moves. The possible third moves we defined earlier. We are going to evaluate how good the move is, and then we're going to search through them all and find the best one. And because it's White's turn, we're going to say that the best available score is minus a huge number, and then we're going to repeatedly check whether our move, the score of the move we're looking at is better than that or worse than that, and we're going to remember the best move, and then we're going to print the better move. And when we do that, we find that if you look ahead one move into the future for White, the best available move is to take the black pawn. This is correct. It's not optimal for the game as a whole, but it's optimal when you only look one move ahead. To do better than this, we need to introduce some kind of pre-search. We need to introduce the idea that the opponent is going to respond, and what matters is not the score after one move, but the score after 2 moves, 3 moves, 4 moves, 5 moves, as far into the future as we can go. No, you can play a perfect game of chess if you evaluate your positional tree all the way to the end of the game, but it just gets too computationally expensive. If you want to evaluate 5 moves into the future, and you've got 30 possible moves at each time, you need to evaluate about 30 to the power of 10 positions, which is a lot. So we don't. You're always limited by how much computation time you have. Yeah, and that's also why I care so much about speed and mention time in library. So pre-search. To play well, we should ideally search n moves ahead for varying n, and we should find the best move taking into account that white players are trying to maximize the score and black players are trying to minimize the score. And white and black have alternate turns. So you get a tree that looks something like this, where one player makes a move, another player makes a move, another player makes a move, and then you propagate backwards up the tree the best possible score. So in the bottom layer, see my mouse? Yes. So this doesn't actually represent the current state of the board because the current state of the board is too complicated and has a high branching factor. In this tree, this row, so 2 moves into the future from the initial position, has a value given by the maximum of the values that it leaves. So here, the max of +4 and +3 is +4. So at this position, white would choose a move that would choose that move rather than that move. Then you propagate back up the tree, and black in this position would want to minimise the score. So out of these possible moves, black would want to pick that one, and then from the root position, white would want to maximise the score, so they want to pick that one. And this ultimately finding the minimum and maximum value in the tree is called min-max tree search, and it's the simplest variety of tree search that works for chess. Okay, so I'm going to reprint the board position as of the second move. I'm now going to define a search function that searches for either player and searches to an arbitrary depth. This search function is going to take a board, it's going to take the depth to search to, and it's going to take whether or not the current player is white. And the base case is, if the depth is 0, we should return the board and the evaluation of the board. That's evaluating our leaves of our tree. And if it's not a leaf, then we want to search through all of the branches available and find the minimum if we are black and the maximum if we're white. I'm not going to go through the code in detail, you just have to sort of trust me, we'll read it quickly. And then we're going to check what's the best move if we search one move ahead. This is in theory the same result as we did earlier. And it is. White pawn takes is the best move if you search one move ahead. If you search 2 moves ahead, white pawn takes is also the best move. If you search 3 moves ahead, it takes a little while. And the best move is white bishop moves out to threaten the king. Which is probably a better move. The further ahead you search, the better your program will play, but the slower it goes. So at this point we have a function that will take a board position and return the best move, given the depth to which you want to search. And this means we can define a little loop that goes and plays a game. So we'll start out with the initial board, we'll loop over up to like 1,000 moves into the future, and print what turn we are on, and what the score is, and we'll print the board, and then we'll check whether the king is still there. And I know people in the room who know chess will kick me slightly. We're just going to search whether the king is present or not to see who won the game, which is a simplification of the rules, and I'm aware of that. So if we run that, where's the output gone? Let's change the search depth to 1. So this will result in a very search depth is 1, and I run that. It will work. It should work. Oh, I need to stop the execution and then run it. Okay. So here we go. Here's the entire game of chess. So turn 1 is it decides to start by moving the knights out, which isn't the best beginning, but we're only using a search depth of 1, so it's not very smart. And then, because we're only using a search depth of 1, and there's no concept that the opponent can play in response to your move, it plays a very aggressive game of chess. So it doesn't last very long until, in the end, the white king ends up taken, and the game is over. And it lasts 66 turns, which is about the same as a professional game, purely by coincidence. If we crank up the search depth to like 2 or 3 or 4, we get much better play. But I wanted to run fast. I suppose I could show you it, running just for a little bit. Search depth of 3. We're passing in whether the card player is white or black there. Here we go. Ooh, sorry. So it doesn't seem right. Okay. Yes, sorry. I changed the depth in the wrong bit of my code. It's the hazard of trying to look at the audience while editing. So here we have a game where we're doing a search depth of 3, and it plays a little bit better. It's still not as good as a human. To get better than a human, you need to search for greater depth than 3. At least to get better than a good human. Not all humans play to the same standard. Okay, so at this point I'm coming to the end of the talk. This simple demonstration of how to write a chess engine is missing out checkmate, stalemate, castling, en passant, and 50-move rule. This can all be added in, but I wanted to make the chess engine simple enough that it would fit into 30 minutes. And there's a huge amount of optimization that's possible from this simple board representation. And there's a small amount of spare time, not very much spare time. Okay, so I'm not going to talk about the extras. Thank you for listening. Any questions?
We are at the end of the session, but since there is nobody in here after us, because we now go to lunch break, we do have time for a few questions if anybody has any.
So, how many moves ahead did your engine look at the one that won the competition?
Okay, so the question is, how many moves ahead did my engine look at on the competition? In the competition, we agreed that we were going to have one 1 second move, and I would normally end up searching 5 or 6 moves ahead in most positions, but some positions I'd search 9 or 10 moves ahead. The use of alpha-beta tree search rather than min-max tree search makes a huge difference to the number of positions you have to evaluate. In the limit of lots of moves ahead, it means you have to evaluate roughly the square root of the number of positions, so the exponential blow-up is less bad. And I spent a lot of time optimizing for speed. So 5 or 6 moves ahead. I probably could do a demo of my actual engine playing, but I should probably take another question instead, if there is any. Yes, in the middle of the corridor.
Have you ever looked into Zorbridge hashing?
Zorbridge hashing. Yes, so I implemented Zorbridge hashing for my main chess engine, but found that Python's built-in hashing goes faster, at least in Python. If you're writing a chess engine in C, which is the normal way you write a chess engine, Zorbridge hashing is much faster. It is really nice.
One more question.
In the spirit of open source, after you beat your brothers, did you share your code with them?
Yes, we agreed that we were not going to look at each other's code until the competition was over, and then after the competition was over, we all had a good look at each other's code. My middle brother is at the back, waving his hand. He chose a radically different way of designing a chess program, and it was interesting looking at how we all approached it. Because we agreed that we were going to write our chess programs without looking at any of the existing literature. We were going to invent everything from scratch. Which made it more interesting. We wrote bad programs.
And I think that's all we've got time for right now, so please join me again in thanking David.